Wow, hi. Thank you for having me. Good afternoon. My name is Ruth Wetters. I'm a data scientist at Knight Frank. I'm going to talk to you today about the research that I've done into how we can use network algorithms to understand global connectivity by using flight data. So firstly, just a bit of background about the company. Knight Frank is best known as an estate agent, but in fact, we are also a global property consultancy with offices in 53 territories. I mention this for two reasons. One, we are at spatial data science and we love maps. And secondly, it's very useful for me personally because I came to spatial data science relatively late in life. I didn't study geography or maths. My degree is in Chinese. So it was really bad planning graduating in 2020. And I never thought when I stuck that in and decided to become a data scientist that I would still get to work on the kind of global problems that I get to think about now. So what kind of questions are we asking? I had a bit of think about this, and maybe I overthought it, but I think the question that we're fundamentally asking is, what does it mean to live a good life? And I think you can start from housing to answer that question because it's so fundamental to the way that we conceive of and experience our lives. You know, where do you want to live? And why, and when, and with whom, and how? And then we also have to think about bigger things like, well, where are people working? What do they do for fun? How do they get there? How does that change across their lives? And then you then have to get onto bigger questions like, well, what's the global economy doing? And how can we prepare for the future? So I've put these bubbles up because that's our view as a firm and how we categorize our different activities. But fundamentally, the thinking that we're doing is about people and their environment. So what does that mean for us in data science? It means that we get to think about a whole bunch of things and we run the whole gamut from descriptive through to predictive analytics. So an investigation might start from, what's going on with the boomer to millennial wealth transfer? Are we still racing for space? What is the grey belt? And then that would naturally lead on to what my colleague would call crystal ball questions. Now, I think lots of us have a well-earned skepticism towards the art and science of prediction, but we do attempt it, and we do our best to make predictions that we can stand by. Mostly we use Python, but we're always curious about new tools that we can learn. And, quick plug, lots of our research goes out in print and online into various publications. So these are our print ones, which are annual. And this research in particular came out of the Wealth Report, which is our annual publication looking into the ways in which ultra-high net worth individuals have changing needs and priorities and how they're using their capital. So we were trying to write about the impact of COVID, and we were like, well, how can we approach this interestingly? And I think particularly we were interested in connectivity, and as a very international group, you can ask, where are they? Where do they want to be and why? So I thought it would be a good fit for network science. Now, hopefully some of you have seen something like this before. I've heard that it looks like a brain or a galaxy, but I think that's just the black background. It's a network graph. This one is from Wikipedia, and it's an early map of the internet. And the thing you need to know about network science is that there are two types of information here. One is nodes, which are points, and the second is edges, which are relationships between the points. And it's really useful for complex data. So network science has all sorts of applications, for example, disease modeling, transport modeling, cybersecurity, fraud detection, how do organizations work? Quite often it's spatial and quite often it's temporal, but they're not necessary to understand the data. So if I told you that I was going to visualize all of the flights that took place in December 2019, you might expect to see something like this. It's a photo diagram. I think it's pretty, but my issue with this is that I think it's not showing the detail very well, particularly. Europe's kind of just a mess, and then by extension, we can't see where exactly people are flying to. So even though you've got the overall pattern, I think that a visualization should show you something at the first glance, but also reward further inspection. And I don't think we're achieving that here. So we wanted to try something different. And so I decided to use Gephi, which is a free open source network analysis tool. So we start from nodes and edges. In this case, my nodes are airports and my edges are flights. And then if you decide not to visualize based on the spatial element, so forget maps, then you're already making a lot of decisions about how to visualize, which you weren't making before, which is a great opportunity because it opens up things like position and size. So you can show the same data in 6 different ways if you've drawn out different aspects of it mathematically. But we can see some commonalities here, right? We've got the kind of 3 clusters, which we think are Europe, North America, and East Asia. We've got some airports that didn't see any flights in December 2019. And then we've got some kind of arms and appendages coming out, which suggest the incidence of a kind of area that's connected to the whole by one regional hub. And so the one that I went with was this last one, Force Atlas 2, because it's pretty tolerant to large data sets. We're on 1 million rows here, which I know is not many for some of you, but it's plenty for me. And it's also got loads of hyperparameters that you can tune to bring out the aspects of the data you're interested in. So if I spread it out a bit, then the next thing that I want to be doing is getting some more detail about my data. So I'm going to use this thing called community detection. And I'm going to run this algorithm, and basically it will highlight nodes which are groups of nodes which are more connected to each other than to the wider whole. I found some interesting things when I ran this. Firstly, I would draw your attention to the fact that even though the spatial data was not explicitly considered here, what we've ended up with does look like a map. We've got kind of Europe, Africa, and Asia all in the right places. We've got America off to the side. Some notable exceptions. So this violet one is Iceland. But yeah, overall, I didn't expect that. And then the other thing to notice is that with the 3 big clusters, within those we've got 2 distinct communities. So North America, we've got the pink and the green. I wasn't sure what was happening here, but when you size the nodes by degree, which is the total number of airports they're connected to, it reveals that actually what's going on is a kind of 2-tier system where rather than acting as gateways into smaller, more regional airports, the kind of larger, more global ones are more connected to each other than they are to the smaller ones. So we've got this kind of, you can see the global network, and then you can also see specific regional activity. So just to confuse you, I've rotated it and changed the colors, but I'm going to filter it so it's a bit easier. And in terms of COVID trends, what we see is that in December 2021, our clusters have got a lot smaller, denser, and further away from each other, which is consistent with what we'd expect when international borders were closed. And we can see that some recovery in 2023, but we can still see the impact of that time. And then, how big is the screen? Pretty big. I'll just tell you. So the things that I'm interested in are that the node which is consistently closest to the center is London Heathrow, which is very useful for us in London. I was surprised by how close Dubai and Doha are to the European cluster, even though they are also their own regional centers. In East Asia, we can see that pre-COVID, the main hub airports were Bangkok, Seoul, and Tokyo. And since then, we've had the resurgence of some Chinese airports, which are now keeping up. And in North America, the thing that surprised me was the prominence of Toronto, which turns out to be a massive gateway airport for people traveling into North America, which is why it's closer to the center, implying closer links with Europe and East Asia. And one other thing we can do is isolate ego networks, which is, if we're interested in one particular airport, we can just see the places that they're connected to. So this is Heathrow. And we can see pretty good coverage of all the clusters, apart from they weren't flying to China in 2021. And so in terms of what this would look like in print, this is slightly different data, visualized slightly differently, but hopefully you can see some of the same structures. And the things that we added here are a measure of eigenvector centrality, which is a weighted measure of interconnectivity, which we use to rank the cities there, just to see what the rises and fallers were. And we've also got some explanation from our sector experts with decades of expertise. And again, quick plug, if you're interested in this, you can see it and much more of our research output at knightfrank.com/research. Thank you for your attention.